Hello, everybody. It's a great pleasure to have Professor Je-Geun Park with us today. We've been collaborating, we've been talking with each other for quite a while now. And then I met him just 2 months ago, I think, in Aspen, in Colorado. And we were the 2 Koreans there. I guess there were probably more, right? And so I said, why don't you come by and give a colloquium talk at QNS. And so I'm really glad that this worked out, and thank you very much for making this happen. So let me introduce him a little bit. Je-Geun got his bachelor and master's from SNU, and then moved to Imperial College in London, where he got his PhD. Then he did 2 postdocs. The first one at the Laboratoire de Magnetism near Yale, that's the Grenoble Magnetic Field Laboratory. Sorry, I slaughtered the French on that one. And then a second postdoc at University of London. And then in 1996, he became assistant professor at Inha University, which is here in Incheon. And then moved to Songnam University, where he moved his way up from associate professor to full professor in Suwon, also close to here. And since 2010, he's been professor at the Seoul National University, where he was also an associate director at the IBS Center for several years. Right. Je-Geun is a fellow of the Korean Academy of Science and Technology, and there he is actually taking quite a leadership role in helping shape Korean science. For example, inviting me to a joint workshop with Max Planck in the fall, which I'm looking forward to. He got the Korea Science Prize. He was also a distinguished professor and SKKU fellow, and also a fellow of the Institute of Physics, which is a UK institution. His research interests lie in magnetic materials with strong correlations, and there particularly he's interested in the discovery of new materials, particularly 2D van der Waals materials, particularly magnetic materials, and topological properties of these materials. And I asked him, so obviously he's not an STM person, right, but he's a little bit broader than our typical interests, but I asked him to give us an overview of 2D magnetism. And so he will tell us about van der Waals magnets, a new platform for 2D magnets. Je-Geun, thank you. Let's welcome.
Thank you very much, Andreas, for kind introduction and also invitations. It's my pleasure to be here. I gave seminar online last year, but being on the side is a completely different impression. Good impression, I have to say. My talk, as Andreas mentioned, is going to be very, very non-scientific, I could say. I'm not going to give you any sophisticated equation or any sophisticated idea. It's about how I came to this idea, how I carried out, how I have arrived at this particular moment of my life. Interestingly, I spent my last 40 years doing science. I started my career in 1984 as SNU as a young student. Obviously, as a physics student, I had big ambitions, but life is not kind to you. There is a small high, but big, deep downs. Not single, many downs, right? But nevertheless, you persist. Right? Each ups and downs and event in your life in 4-dimensional space and time. And if there is a non-scientific message I want to come across today is, as any human activity, science is connecting dots. So my talk intends to engage with younger people, not seniors, sharing my terrible mistake, and also some lesson I learned. And I try to be honest, humble enough, so you can see how low I was at some point, and probably give you some motivation, I hope. Right? And so for first 10 years, I was trained to become professionals, undergrads and master and PhD. And the last 30 over years, I mainly worked on 3 topics. My PhD and all postdocs was on inelastic neutron scattering and feasibility of excitations and epiphania. So I did a lot of neutron scattering, and And I'm still doing that. My next 10 years on so-called multi-term materials, I did a lot of structures and spin dynamics things. Again, using neutrons and X-rays. And that was about time I decided, well, I was invited to come to SNU, and I was about 45. And I don't know how many of you reached that particular age of 45. My 45 was a mixture of joy and disappointment. Joy, obviously, I got the job I wanted all my life. Going back to alma mater was a big honor. And disappointment, I don't regret whatever I did. I did good science. Otherwise, I could not have been invited to SNU professors. But nevertheless, I had a big disappointment. The disappointment I had was whatever I did, and any good paper was good paper, but I somehow felt I did not own that science. It was very strange feeling. I did the published paper in Nature Material, whatever, but I come to certain realization I did not own my science, and it was very uneasy feeling. Deep in belly, I become uncomfortable, and I was asking why, and I come to conclusion that particular science did not start from my question. That was the moment I decided to do something strange things. And the story which I'm going to tell you today is basically about that particular journey I made.
Maybe click on the screen sometimes.
Right, okay. About these things. So around 2010, so it is moving to a completely different place, no matter where that place is your alma mater, is good reason you have to start anew. Once you move, a lot of you move from country, right? Then you know what they mean. You basically become different person, okay? Different person to me is different science, okay? So around 2010, when I was 45, I decided to do something completely different. It was a crazy idea. A lot of my good friends gave advice. Don't do that. Don't do that. I know you. It's not going to work. Against that harsh criticism, I persisted. The reason was, as I said, I want to own my own science, and there was a big risk, but I was crazy enough to take risk. Secondly, I had enough confidence in my judgment and my idea. I'll tell you why. So, whole my story today is about that journey. Something like 15 years journey I took. Believe me, I went through deep into negative side of your psychological cycle. But as a scientist, I know that have to be something I have to accept. And I often tell my people, when we got our paper rejected, I tell them, even that moment rejection, you have to enjoy to become a scientist. And I tell you what I did. So basically, my journey is about all these 4 papers. I know no one come to this QNS give a talk on these 4 papers. They're good paper, but you probably say that's not good enough, right? That's the point. When you start something new things always small beginning. Obviously, I was ambitious, right? But your ambition doesn't guarantee that you're success. And so this was my first paper, scientific report. I'm not going to tell you about the journals. So, as I said, I started this idea about 2010, and then there was a number of struggles, and I got some real data about late 2011, early 2013. I wrote the paper. Submitted the paper in 2014. Rejected. and then paper was ended up with in scientific report. And there was 3 more paper I wrote. And that's basically most important paper ever I wrote, because that's basically beginning of whole area I started in 2000, well, officially 2016, but unofficially 2010. So I'm going to tell you about my small beginning, and that small beginning is actually shown in this model I have in my office. The idea I had was inspired by graphene. The difference I made, twist I made in that idea was I want to make carbon to become magnetic. So I want to have magnetic version of graphene. Why that important, I'll tell you later. And starting from that, it took a couple of years. That was okay, but it took longer and more emotional struggle to convince community is worthwhile. And that's the best story. Okay. And then I'll tell a little bit of some more success we made in Outlook, including some personal view on how the field is going to change. Unlike most of you who are expert STM, specialized in tools, I'm more software all-round player. I'm more material oriented. I'll tell you why I was born that way. So there is small difference. Material is most important for me. The reason was, I was fortunate enough to have great scientists as my mentor. This is my PhD supervisors at Imperial College. I only spent 3 years with him. Unfortunately, he passed away soon after I returned to Korea. I couldn't have benefit of having more insight and discussion about my life and my science. But 3 years is long enough to learn something important about science and life and scientists. He never actually taught me science. If you know the UK system, it's all about tutoring, mentoring system. He made sure that he spent at least 1 hour a week with me. Believe me, he was extremely busy. He was a vice president of Imperial College. He was a member of Royal Society. He was the president of France and Taylor, one of the biggest publishers in English-speaking world. So he was super busy, but he would make sure to spend at least 1 hour with me. Everything he asked about my science question. And spending 3 years under his guidance, he's known for spin glass, and he's the person who coined that spin glass. And all the training, direct or indirect, gave the impression that material is very important. He always called me JJ. Je-Geun is too difficult Korean name for him to pronounce. Whole my time with him, only once he made the effort to pronounce my name correctly. Otherwise, he will always call me JJ. And also, he called me that the science I'm doing is fishing in muddy pond. Okay, it's a serendipity, basically scientifically, and that instilled deep into my heart love of search for new material. And that was my realization at 2010. I want to have my material. Okay. So that training gave me perspective about science, material view. So let me share my material view about 100 years of material science, or so it's science, physics, or conventional physics. And if you look at the whole 100 years of science we doing, there is a star material. Material symbolizing the 1 decade, if not 2, 3 decades long scientific effort. Spin glass, my professor's is creations. Fermion was subject my thesis. And then there is multiphysics. I spent 10 years, graphene, etc., etc. Material is so important because theory theory guys build up their theory based on this experimental observation. So we are inspired by theory, but we inspire them equally. And that's language we use. And I had big ambition in 2010. I want to have something which I can own. I can tell this mine. So that was magnetic graphene. Easy, graphene, magnetic. Let me share my rationale behind this small idea. It's small lessons about magnetism. Magnetism is all about dimension, spin symmetry, and lattice. It's everything. It allows us to build up Hamiltonian. A to Z of science we're doing. And if you look at this three-dimensional phase space, there's a whole lot of the points you can pick up. And my question was, there was one particular window of opportunity, two dimensions. There you can explore something new. And that is part of this whole picture, universe. Why that is important? Well, our understanding is rely on Hamiltonian. And in particular, Hamiltonian, we are familiar with asking question, what happens if you cool the system down? Will there be any finite temperature transition? The language we have is three. One is the Onsager, Ising, XY, and Heisenberg. And each model Hamiltonian is so important that each of us, at least I spent at least 2 weeks of my lectures as a graduate student at SNU learning Onsager solution. After 2 weeks of derivation of a complicated expression, you end up with this particular formula. Transfer matrix of Onsager's technique allow you to get this number or this equation, and then basically describe what happened in black and white binary world, Ising system. Okay. Yet there has no experimental test of Ising model using real 2D material. That was my question I had in 2010. So I want to have a material which I can use to test Ising last Onsager solution published in 1943. And people challenged me. That wasn't correct. Obviously, this is a big question, so people tried much older than me, especially when Kenneth Wilson revolutionized our language of universe using renormalization group theory. People start to look at this critical phenomena in honest, using different material in 70s, even 60s, exploring universality of phase transition. And they call test. You accept that test, but that's using true three-dimensional material. They're all three-dimensional. Nowadays, people actually produce very thin sample using PLD and MBE. Especially in bauxite community, this is one big business. They have different agenda too, right? But yet, no one did what I wanted. I wanted to test Onsager solution with very 2D material. Okay. So even when I proposed the idea, people challenged me. I was wrong. I didn't care because I was so confident that I did a long research survey to come to the conclusion that no one did that idea experimentally. Here comes my idea. Magnetic graphene. Graphene of magnetic ion. It was so crazy, but I thought it's useful because in my field, so-called strongly connected electron system, we need a magnetic because once you magnetize system, then these type binding model, non-interacting model is useless. basically you go to how about you, huge quantum fluctuation, and obviously this is a big challenge, but there is a bonus. Bonus is you are bound to find some very weird quantum phase. Okay, if you care about something new, that's a fantastic place to start with. Okay, and that was my rationale behind. How difficult it will be, I didn't care. I had 10 years, and I was brave enough to be stupid. You have to be stupid to want something. I didn't care what people call me. Stupid, crazy, whatever. I didn't care. I just want to do something. And I was confident enough. If I can find the material, I can show that dream comes true. And there was a big risk I had to take. I'll tell you what risk I was taking. So my whole life, starting from my PhD, I was so familiar with Hamiltonian. And to study Hamiltonian, I have been doing neutron scattering, index neutron scattering. And if you do index neutron scattering nowadays, you get terabyte data. And it's an actual test of your idea about system, spin path. Okay? We did an experiment on nickel PSG, exactly the same compound I showed at the beginning of my slide. But now, my student code line something like 50 different crystals with total mass about, I think it was about 2 to 3 grams. It was crucial. Without this, you can't do any index neutron scattering. Here is the point.
They're all aligned with each other?
Yeah. You can stop me anytime you like. I just want to come out of my comfort zone using 2 grams of sample. We often call it rule of thumb because my sample is big as my thumb. It was a pride I had as a young kid. Now I want to do something on sample as very wide as 10 micron monolayer. Okay? If you don't realize how stupid I was, here is some analogy I'm taking. So in terms of size, I'm changing sample from 10 centimeters to 10 micron. Well, 1,004 degrees. Well, that's not big enough. But in terms of weight, I'm changing sample from 3 to 10 to the 17 grams. 10 to the 17 is this. So this is a beautiful campus. My campus. So this is something. Yeah. So basically, I'm trying to see my campus high up in the sky, something 1 kilometer, and seeing this my office. The other crazy thing is 10 to 17 is number of grains consumed by whole Korean for 1,000 years. Okay, that's the number I had to face. And my friends, in good sense, try to point that risk. If you put your life at balance, your old is 1 out of 10 to minus 17. Will you take that chance? Yes. I just want to own my science. And I was so desperate. I want to own my science. And that is why we emphasizing on the importance of asking questions. If you don't ask questions, nothing will start from your idea. So I encourage my students to ask questions. I encourage myself to ask questions. And question is very important. So let me tell you what mistake I made to come to realize this particular idea of magnetic rock field. And my vision was very clear. It's very easy. No one actually can say this. If I can find the material, I can do these things. I can basically reduce thickness and go to monolayer and see whether on-site solution is correct. Or you can, interesting in 2016 is a bit early, but I didn't use word moire, but at least you can do something freestanding and twisting. Well, I didn't know that, but at least I could imagine that these effects of straight heterostructure is enormous opportunity for all of us. The only problem was there was no sample fit that bill, and all my friends tried to point out, even if they accept my idea, and they gently pointed out that there is no sample that you require. We started with oxide because I was so familiar with oxide, and these oxide, interestingly enough, has a magnetic honeycomb. Okay, so this is made of a magnet. And I had a student, Sang-Hyun Lee, who was very talented material scientist, and we tried hard actually. Cleave them. And if you take cross-section of TM, it's tantalizing layered compound. You can easily imagine that you can break this bond, okay? And here is a big mistake. Don't trust your supervisor. It's a lesson.
Obviously.
I made a big mistake. I don't know why. So the first lesson I took had at my solid state physics course as a fourth year grad student at SNU was covalent bonding is strong, right? You never break, right? These are the oxide. These are all looks like a layer, but they are covalent bonding. And here I'm trying to break it. Okay, so I was crazy, right? So one day my student keep coming back saying, "No, it doesn't work. It doesn't work." I asked him, "Try again." Year passed. We almost gave up. With hindsight, the idea shouldn't work with covalent bonding, right? I almost gave up that idea. Then there was a epiphany. So I did my first postdoc as Andreas said. I did my first postdoc in Grenoble. If you haven't been to Grenoble, I recommend you should go there. It's a beautiful place, especially in winter. My office is in scientific polygon and in Ole called Linear. So I work in both places, Linear and CRTPT. Now it's a single analyst. As a young, I was 26 then. As a young single Korean living in Grenoble, science is the only things I can do. I couldn't ski, so reading books, reading papers, reading. I read books by De Jong, he's Dutch, from Phyllis Lab on distilled French materials. And also I realized something very important. Some first dot in my scientific career. I somehow began to join the dots. One dot in my first postdoc, and then soon I realized I need to connect that dot in beginning of my scientific career. That was my first paper, my master thesis. It was non-oxide magnetic material. So I started my career with something which I began to familiarize with. So that was good enough motivation. Another fortune I had, I read a lot of paper, but Andres, I had a long discussion about the scientific culture. Culture is very important. In France, my group my project, I worked on mangan acetate, mangan 12 acetate, and I was one of the first person who measured the quantum coherence in molecular magnet in mangan 12 acetate. We spent months after months relaxation. The fortune was in this group where I was working with, I was basically interacting with French chemists a lot. So I saw the chemists eye to eye. There is no difference between physicists and chemists that we have in here in Korea. The one particular paper, I never met him, but one particular paper I read was written by Raymond Bragg. He's well known in organic chemist, professor in And my focus, after realizing those few things, suddenly prompted me to go back to his paper. And his paper is all about transition metal phosphorus, chalcogenide, sulfur, selenium, tellurium. And his paper was basically Bible for me and all my group. In his paper, you can see that actually they have honeycomb magnetic and van der Waals, and there is already everything you need. There are antiferromagnetic, semiconductor, van der Waals. Okay. I could have taken completely different route, even if I started with the same idea. But I was hooked by one particular observation pointed out in his paper. In his paper, he pointed out, if I work on iron, then I basically realize the Ising system. And if I work in nickel, I realize the XY. If I work with mangan, I will realize Heisenberg. You remember a few slides back, I emphasized important Hamiltonian and why I was interested in this particular system. And therefore, I couldn't do something else. This is basically system I had to work with. And I had a very nice Indian postdoc then, so I asked him to make sample, and recipe was there, basically. Within a few weeks, he basically made sample and discovered that actually sample wasn't reported in that review paper. But I asked him to bring the scotch tape. We together type extrapolate. After a few minutes, I asked him to put the sample on top of that head of IBS then and sample it for transparent. Fortunately, that was highest moment I ever had last 10 years. My idea works. And that brought me another big problem. You remember, I was working with 3-gram sample as big as my thumb. Now I have monolayer. Virtually, I'm powerless. I didn't have any idea what I have to do. All the technique I spent 20 years to master become useless. Neutrons getting no, X-ray no, transport no, because this is insulator.
SK?
Yeah, but I didn't have STM, two friends. So, again, this is humble moment, and I have a philosophy. I have to listen to my younger member groups. And I had a couple of the good postdocs validated me about this scene sample. And Bala was man who synthesized sample, then Ching Tai Ku and Michael Neumann, especially Michael, who spent his first postdoc in Stanford, Tony Heinz group, was very familiar with the graphene things. He basically told me, so when I told him my idea, he basically told me that we have to use Raman. I virtually had no idea what Raman was. The only thing I remember about Raman was, Raman is useless tools for magnetism. That was a lesson I was given in 90s. So I was pretty much ignorant of Raman.
Then how you could be sure these are magnetics when you made those samples?
So bulk we know, bulk are magnetic.
Yeah.
The question is monolayer.
Monolayer, yeah. How you can confirm these are magnetic?
So that was my beginning of my horrible journey. I'm going to share with you. I have no idea. I didn't know iron PSV I knew because this is Raymond Brexer is Ising. If it's correct, you have to have stable monolayer magnetism. But everything else we didn't have any idea. I expected nothing is going to work.
Because I raised the question because should we accept for this 2D magnetism that conventional long range magnetic order, magnetic, definition? That's also my question.
You touching some very sensitive issues, but this is a good question. How much of the understanding we have about about magnets mostly came from three-dimensional material.
Yeah.
Can be used for two-dimension.
Yeah.
So far it works. But I believe there must be some corner where there must be breakdown. Otherwise, discovering two-dimensional magnet is not new. Right? But I'll tell you what we've been discovering recently. So this is one of the first, my humble lesson give my junior members, 3 postdocs. They basically taught me why that have to be used, including AFM and Raman. We also measure the tunneling current on monolayer using conductive AFM. All these tools was new to me. Now I know a little bit, or I can pretend to know the details, but then I virtually as ignorant as any undergrad student of these things. And so lesson number 2 is we have to be polite to our junior people and try to learn something from our young student postdocs, because they are better people than I am, right? So obviously when I started, we do everything. It was crazy, random process. If one day I was desperate, didn't have an idea. Next morning, I suddenly have an idea. I tried to think about how I can do that. Such like random process, okay? But obviously, from the beginning, I had more interest in this particular Ising PS3. Good. Only that is going to be justify my journey. Otherwise, no one was going to believe it. So here is what we did. So my goal was proving that monolayer IPS3 is magnetic. Nothing more, nothing less. Here, I was fortunate enough to have a good friend, Je-Geun. We knew each other personally, but we never collaborated. It took a couple of years actually to convince that Hanishik that it's going to work. He was so nervous.
So
He never worked on magnetism before.
He did the Raman?
He did Raman. He had a good set of Raman. Actually, one of the best in the world, I think. So I made a big effort I didn't bribe him for record. But it is, other than bribe, I made all my charm offensive to him. It's going to work. You should just measure, and the rest I'll do. That was the deal. Okay. His group do the experiment, and I will do the interpretation. Believe me, I said, right? He's a senior than 2 years senior than me, and obviously in Korean hierarchy, trusting junior is some risk you have to take, but kind enough he did. And these are the security we measured in our bulk sample, and this is the monolayer sample we produced for Raman experiment. And the Raman, unlike my lesson I had at Seoul, is actually sensitive to magnetism through the spin lattice coupling. Okay, so we measure the spin lattice coupling. So this is measure of the parameter ratio of the left and right, and you see that this signal collapses on top of another. So you basically proof of universality. Magnetism is stable than monolayer. Okay. I was so excited. I'm so happy. I'm still very proud of this particular discovery. And that is basically a short summary of my first 6 or 7 years of my journey, coming to this particular 4 publication. Not in a paper published, not excellent journal, but proud enough that I own this science. And year later, a group in US worked on ferromagnetism. This is a very interesting twist of my fortune. If I go back to my beginning of my this journey, I could easily go to ferromagnetism instead of anti-ferro. Ferromagnetism is much easier because you can directly measure Moog signal. You direct measure of the Moog. But as I said, I was so ignorant of the optical truth. I knew the Moog because I teach associated physics, but I wasn't that familiar with Moog. So these were the births of the Pandora's egg, both anti-ferro and ferromagnetic. Over the last 6 or 7 years, number of dozens of samples reported for various properties, and I'm very proud of all the samples marked in yellow. Half of them came from my group. And now we can realize that all the possible 2D lattice, you remember, in magnetism, lattice is very important. And the field becomes very active now. So with that, let me go into last chapter, or more recent chapter of my journey. Like any part of the last 15 years of journey, every moment is uncertain, unpredictable. You have to take risks, but at the same time, you have to be humble enough, admitting that you do not know. So the way how I've been doing is I try to think about the question. I discuss that idea with good people, friends who can share my stupidity, and ask them questions. And slowly they help me to refine my idea and also how to do the experiment. I'm going to share the 3 parts of my journeys. First part will be very active field. We are interesting and everyone else interested, so-called light-matter interactions. And the second part is spin translocation. These 2, I think, will be major thrust future directions of the Pandora's egg. And third part is some technical development we're doing for the last few years for other purposes. So when I had this started this whole project, I had a game plan. How I like started and how I'm going to publicize. I had a master plan. But like anything in life, nothing works according to your plan. Every plan breaks down, but something works. So I had the opportunity to write a review paper soon after my discovery in Nature. And this is basically a picture I prepared. We set my student and everything there. You can study the basic Hamiltonian and gating strain, proximities, light-matter interaction, or basically I get. And I gave a long list of what's possible, what's important. Amazingly, I basically categorized the 4 important interactions: material, fundamental issues, device, and quantum topology phase. At least half of that sub-topics have been either tackled, solved, or done, or finished by my group and others. And that much is competition. It's so fierce competition, but you have to be in the game. Light-matter interactions is a very interesting interaction because this is 2-dimensional. If you have any excitation, fundamental quantum particle, you have to have a dispersion. Okay? And when you have dispersion crossing each other, then you're going to have an anti-crossing. You're bound to have coupling. Coupling between different quantum particles is basically the best opportunity of new science. It's not of controlling ground state. For 2D material, obviously 1D is the best because everything is confined with line. So there is a maximum overlap. But we know 1D is boring. Nothing is going to happen. No static order exists. 3D is complete opposite. If you have spaghetti running along 3 dimensions, every you have tried to throw the spaghetti in the air, no spaghetti is going to cross, right? But in 2 dimensions, there is a marginal proximity. And that proximity amazingly produces very interesting idea, magnetic extons, extern form magnetic bound state, and noble state, including local state. Obviously, there are many papers published in this topic. Let me share one particular success story we had. This is about the exton we found in nickel PS3. Exton is not new. New is this exton is strongly temperature dependent, which means this exton is coming from S2 level. Okay, electron structure cannot have temperature dependence. So any two-level system optical allowed have to be bright exton or dark exton. You cannot make bright into dark or dark into bright. Okay, but as you can see here on the left, this is PL data taken by Hyun-Sik Seoul University group, shows that exton become absent about 100K. That's below emission. So exton
So-
become,
Then the structure change.
no, I don't think so. So this is, I tell you some problem we have. So electron state at 2 level is fixed, but somehow exton is bright at low temperature and dark in high temperature. The only change is spin state. So spin degree freedom coupled to electron state. So this is a nice example of exton coupled to spin degree freedom. And you can check that idea using optical absorption, which is more bug sensitive. You can do. But there are a number of interesting observations we made. First, this exton is so narrow. Resolution, the line width is about 400 microelectron volt. And there are two things you have to remember. This is 10 times smaller, narrower than impurity field. Secondly, this 400 microelectron volt is much smaller than your thermal energy. Thermal energy at 10K is about 11 by about 1 millielectron volt. So my line width is half of that. How can you beat that thermal fluctuation? Let alone impurity fields. That is the question. I do not know the answer. We just made observations. And then this is spin entangled extons. And second point is there is a bound state. This bound state, exton coupled to the phonon. Not one bound state, high second bound state. And now people in MIT you getting discovered there is about something like 13 bound state of extern and phonon. 13. Not just one extern phonon, but one extern and 13 phonon. I don't know how it works. Anyway, that is our interpretation. And there is strong polarization. And these extern, we know through the many-body calculation, we know this is coming from two states. But two states are not just two states, these are the many-body quantum entangled state, so known as general singlet entropy state. So these are the exciting new states. The old observation need answer 2 years, well, paper was published in 2020, and 4 years after, we still struggle to understand this problem. This is open question. And spintronics is another major direction. Obviously, there is a lot of the uses opportunity, application, or otherwise. There is a several attempts using 2D binary magnet for a number of things, and there are many more. I'll probably skip this part because this can be a long story. But let me share my last idea, which we've been just finished. And this material, I think, offers entirely different rules of game, what I call quantum quad. So there are already several 2D materials with different ground state, magnetic, superconductor, topological, multivariate. And these are basically two-dimensional quad. Okay? And we know if you build up three-dimensional system with different atoms, you come to completely different ground state. And if you build up system with two-dimensional card with different state, guess what we will get? A huge opportunity. And this is what I call playing quantum card. Any number of these sequences. I don't underestimate the difficulty of a technical issue. Sure, there will be huge technical issues. But still, At least theoretically you can do. So one big technical challenge we had was how to build this idea into reality. So last few years we're building some recipe of making these things into reality. So let me share my idea about this. And it involved two students, like one student, one who left group now is in Michigan, and Gi-young is my current student. So all the 2D material, magnetic graphene, Bardet graph, whatever, use a number of the polymer. A typical one is so-called PPC TRS diagram. This is how you people make Bardet.
So here's some more.
I'm so excited.
I see.
But this method, music voice, oh, I become so emotional.
Unfortunately, it's the end of the talk.
Yeah, that's right. So this particular method doesn't work with magnetic graphene or other material. So we, with help of the physics in Harvard, developed new technology, so-called PCL. This is new polymer. It has huge advantage. It has a strong adhesive force. It has downside too. But you can basically increase the size 10 times. Increase size much larger. Here is an example. So we recently reported that you can basically make a bilayer graphene as big as 10-1 coin. Not 100 micron, centimeter wide. Obviously, quality is not good enough yet, but at least we can demonstrate that you can make bilayer graphene in the size of centimeter. The another opportunity is this. We now can pick up basically every non-Van der Waals material. So, and with very clean interface, obviously this is one of the best cross-sectional TM we have. Don't believe in that. This is, we fail a lot. Actually, I still fail a lot to make sample. But we have to now. You can make quantum card. We just open the door. And how we're going to use this is another huge battle. Because there are so many combinatorial ideas. Each heterostructure, I ask my student, they will have to spend minimum few months of their time, if not a year. And I don't waste my student and postdocs time. And that is my big worry. Which one? So, let me conclude my, before finishing my talk, let me acknowledge all my collaborations. Last more than 10 years journey involved a lot of people. Many of them helped me a lot, giving idea, doing experiment, and teaching me the techniques, and criticizing me, and that's very important part of this journey. And we have a strong team at SNU with some of my colleagues, and I rely on basically 5 groups for optical measurement, one at Seoul University and Sikchang's group, and one at Yonsei University Je-Geun's groups, and one in GIST in Jong's group. But we also collaborate with people at MIT, New Delhi, and also Kat and Dave Share, and some theory done by Leon Barnes. And we still do a lot of X-rays and also neutron scattering. And some of the quantum manual calculation done by group at KIAS. But unsung hero are my former and present members of groups. And these are photos taken a couple years ago. Swan now left, and then Eugene left recently to join the Los Alamos. And Kaishan is one member who stayed the last 5 years with me, very active. And these are the former members. We didn't have that many people, but they move on to next step. Seungmin is one of the first who worked on these problems, and Sumin did that nickel magnetic isotopes. Bala was the first postdoc worked on this problem, and Mekko worked a lot to improve our techniques. He went back to UK. So, to summarize my talk, I'm not going to say any scientific statement other than these are basically new platforms for new science. And the area of interest will be involved with scientific academic curiosity, applications in electronics, heterostructures, and many more. As John F. Kennedy said, our imitation is only limitation. Otherwise, there is a huge open field. And that allows us to play quantum card, and how much we can do, I don't know. But as a person who started business in early 2010 with humble, small idea, it's very rewarding, and I'm very pleased that I took that risk. And I should acknowledge my funding agency, National Research Foundation, and also Samsung Foundation. With that, let me thank you all for kind attention. Thank you.
Thank you very much, Je-Geun, for this wonderful introduction. Let's see, students. Students first. Yes.
Can you explain in the iron in the first few slides there's the iron PS3 mangan PS3
yeah.
that use different models. Can
Yeah,
you explain
yeah.
that? I couldn't understand.
That is also a very good question. I don't know how I can start. So you basically expose my limitations, or actually not my own, but actually limitation of our knowledge whole field. So you basically ask me why IPS is Ising and IPS XY and MAGA-PS Ising. Okay. And first of all, let me say this is a remarkable observation. As I said, I spent the last 30 years doing magnetism. There is virtually no other example. You basically replace one transition metal to another, you change the boiler system. Okay. Why it varies? Obviously, ultimately, it's all about electronic structure. Okay, but that is no brainer. For example, iron is not known for strong magnetic anisotropy, right? Yet here we have about something like 33 millielectron volt per iron single line resonance. That's what a record. Okay. Why iron PSV has such a large magnetic anisotropy has been puzzled. At least we made the experimental observation doing PIM experiment and kept down the number. And recent theory pointed out that actually spin-off coupling, the relativistic effect of iron, which has been ignored for many discussion, is key. And I think that is correct. So that's the one. Why nickel PSXY and why MAGA-PS Heisenberg? Again, I said it will boil down to the ultimately electron structure. But easy hand-waving argument, I don't know. It's a very good question, and understand that is also very important. But at the moment, I don't have any particular answer yet.
This is a manganese 2 plus?
Yeah, they are all 2 plus.
Spin 5 half.
Yeah, they are all 2 plus. Yeah.
Other questions? Should we allow Tehi to ask a question? Did you bypass the microphone?
Yeah, first of all, I was quite amazed about the 3 different types of susceptibility as function of temperature. It's clear that experimentally you show that Ising model and.
But I have to give credit to people who worked on this
I'm
problem here.
amazed. I'm amazed. I did not actually.
Yeah, we have to like our junior people, but also people who went before us.
I think maybe I can use that to teach my students for what is that. Okay, my other question is about the quantum card. You mentioned about that the superconductor case about niobium diselenide.
Yeah.
I'm wondering that are you saying that is it, I mean, in two-dimensional superconductor, or just you saying that between interface, the superconducting behavior
There is nothing about it. It's
pure,
basically pure 2D dimension.
that only 2D?
Yeah, you can have 2D superconductor.
Then I'm wondering that when you put on other organic stuff, the superconducting property would remain over it.
Oh, that's another question, $1 million question. I don't know. Until I do the experiment, I don't think I can understand. So what I'm saying is these things is not possible. There is still technical difficulty, but at least some of we did and others did now make it at least is accessible, right? Okay, and now comes the moment that what is the question?
I see.
What is the question? Which question you like to ask?
Okay, thank you.
Other questions?
So basically, from your talk, I know that in two-dimensional magnetic order is stabilized by finite temperature, right? Because at zero temperature, because of moving magnet theory, we have no.
Oh, right. Yes. Yeah. Okay. I didn't actually answer your question which you asked during my talk. So let me go to so let me borrow the analogy of particle physics. Okay? So there is a lot of quantum vacuum fluctuation. Okay. If you have a mass gap, okay, so you have a vacuum, and then if you have mass gap, like in Higgs boson, then you need a certain energy to break that, create that particle. Okay. In that analogy, we have spin wave. To stabilize magnetism, you need to open that gap, mass gap in particle. That will be called spin gap. So stabilize magnetism and finite temperature, you have to open the gap. So that is why analysis is so important.
Okay, so with lowering temperature, the spin gap will become smaller.
Spin gap is an intrinsically electronic structure effect, so it shouldn't temperature dependent.
So in that case, at zero temperature, you should have like magnetic order.
Not every system, only Ising system or material with certain magnetic anisotropy. Because if suppose you have vacuum fluctuation or zero mass gap, then you basically kill any stable particle because there's vacuum fluctuation is going to destabilize. Okay. To stabilize a particular field or state, you open that gap to, it's actually kind of breathing room to have that state stable. Otherwise, all the fluctuation is going to destabilize state. And to have a ground state, magnetic ground state, you need that gap bigger than your solenoid.
Yeah, for Ising, I know because of this is D2, it's not continuous symmetry. So you can have like magnetic order at zero temperature. Right? So you're meaning that for Heisenberg magnet with strong anisotropy, you can also have like.
In principle, yeah.
Okay, yeah, thank you.
Okay, I see there's a question or two in the chat. Can we open this?
Yeah. So there's a question on Zoom from Nassim Kalai. Hello, thank you for your nice talk. I have a curiosity about the rationalize of the different model Hamiltonian between Fe and I and Mn and XSTS3. Can you comment about this? Moreover, have you tried to measure the universality classes for some of these 2D magnets?
Right. So this actually touched the question made by someone else. So rationalizing the different model Hamiltonian, you can do the guesswork. But I think people like me, we just start measuring the susceptibility. That is actually a nice tool to determine whether this is Ising, XY, Heisenberg. But if you ask me about the detailed microscopic idea, you need a friend who can actually do some theory, okay? DFT, relativity, mostly, okay? The universality class is actually, there is a word of caution. So, universal class, yeah, we do, but not professionally. The reason it is that after Kenneth Wilson's 1973 paper and Nobel Prize, people try to do that in many material, but you have to understand the universality class can be only a valid concept very near to transition temperature. How close? You have to use so-called reduced temperature, okay? And that reduced temperature, the universal class or the exponent x, alpha, beta, gamma, and delta identity can be defined in the 1,000 or 10,000 close in this temperature. So to give you a number, so if your transition is 100K, that particular concept only valid to something like 0.01 plus minus. So like 99.99 to 1,000. So you should measure something between 99.99K up to 100K. That's the only valid window, plus minus. That's what Kenneth Wilson told us. That's the quantum fluctuation domain regime. If you extend that idea, you can define the image exponent, but it's not correct. People do, we do, but that's not scientifically rigorous. So that there is a word of caution. And then the second question is,
Have you tried to measure the universality classes for some of these 2D methods?
Yeah, I answered. We did, but as I said, that is not actually honest measurement. But there is a caveat.
Good. Okay. Other questions? You still have the microphone.
Sorry, I want to ask one last.
No, you don't have to apologize. Asking a question is your right. Answering your question is my obligation. So
Thank you. So with anisotropy in SO3 Heisenberg, you actually you're reducing to XY model, right? Can I?
Yeah, that's another very delicate point actually. If you say, so now you're asking, if I start with Heisenberg, I open the gap in certain reactions, then do I go to XY plus? Okay, that's your question. Okay, yes and no. So that depends on what energy or temperature range you're interested in. So if your temperature fluctuation is larger than the gap, then your system doesn't care much about your gap. So the system becomes Heisenberg. But your temperature is lower than the gap, then obviously that fluctuation is suppressed. So there is a high chance of you seeing the XY model. So low energy dynamics is governed by that symmetry. So there is some kind of crossover behavior.
Okay, thank you. So I can understand that the magnetic order in Heisenberg model with high anisotropy is at low temperature because of XY. You actually
Yeah.
XY.
Yeah.
Okay, thank you.
Je-Geun.
I love actually still asking questions.
So, for playing quantum cards,
Yeah.
how do you predict or how will you decide the ordering?
You're actually asking a very important problem I have. So since you asked, let me share my question. So as I said, I know certain things, but there is a huge amount of area I am not familiar with. So nowadays, every meeting I go, I ask a question, and as I said, asking question is very important in this field. One question I'm going to ask. So there is a few things I'm doing, but I'm not quite sure. I'm still reluctant to put my money on that question. So we're doing some trial error experiment, but I still searching for right question. And once I have a right question, we go directly into the problem.
He doesn't want to answer you. Secrets. Okay, Martin, you have a question? Yes.
Yeah, so my question is similar to the Je-Geun. So, what's the final goal of you? So, do you want to make some the new type of the material?
Right. Okay. So being honest with you or everyone else, I don't know. So everything I showed up to this point, there has been some surprise, new discovery, but overall, nothing new. Basically, we made a new sample, tested all the idea, we showed it works. There is no real surprise. My real wish is I want to make real discovery, like manufacturing one, and then the technique we develop another. But of this point, I haven't made that much new things. Hence, you ask the question what my goal is, I don't know. I spent the last 30 years, or actually include my 40 years in this game. Before my retirement, I only have 7 years to go. I don't know. Every day I'm thinking of this problem, but I don't know. But I'm pretty sure I hope I can make that discovery. If I'm not the lucky person, I'm sure there will be another person who is lucky enough to have idea. Because these are there is saying in my community, 2-dimensional is dangerously irrelevant dimension. This is the right place where you're searching for maximize spatial fluctuation, quantum fluctuation. As you know, the fluctuation actually creates new phenomena. And therefore, I'm very hopeful that there must be something where I don't know. When is another problem?
Well, I think that's a perfect moment to end. Let's thank Je-Geun again. Thank you very much.